Alright, here is a projectile fired at an angle, and it's very similar to a horizontal projectile in that we're going to analyze the x and y components separately. So we have delta x, we have vxi, vxf, ax, and t. And we can say the same thing in the y. We've got delta y, we've got vyi, vyf, ay, and t. And again, for pretty much all projectiles, you should know the accelerations. X is 0, because it doesn't change. There's no forces in the x direction. And in the y direction, we have negative 10 meters per second squared. And in this situation, it says that it is shot at a velocity of 40 meters per second. You might be wondering, okay, where does that go in my chart? Well, technically neither, because the 40 is shot at an angle of 60 degrees. So what I need to do is find out the x and y components of that in order to place them in here. So look back on how to break down components if you need to, but a quick assessment is if I take the sine of 60 degrees, that equals the opposite, y, over 40. That was the hypotenuse. So my y component is 40 times sine of 60. So my y component is positive 34.64 meters per second. And my x is going to be cosine of 60 equals x over 40. So x will equal 40 times cosine of 60. So that's 20 meters per second. And it should make sense that our y velocity is higher than my x because I'm firing it more vertically than horizontally. So I have those in place. If I want, I can say, well, my final x velocity is also 20 because they never change. And it wants to find that our ultimate goal is how far away does it land. So I'm really looking for this. And like most projectile problems, the key is finding out the time. So if we know the time, we know how fast it's going horizontally, that will tell us how far it's going to get. So how do we find the time? Well, we don't really have enough x information to solve for time, but we do have enough y information, because if it says this is landing on the ground, if it's fired from the cannon, which is pretty much on the ground, delta y is 0. It's not changing its height. So we have delta y, vi, and a, and we're looking for t. So once again, we're looking at equation 4. We know delta x, we're calling it delta y in this situation because we're analyzing y. So that is 0 equals v naught, or v beginning, is 34.64 times t plus 1/2 a, negative 10 t squared. And if I do the algebra on this, a little bit of manipulation, I get 5t squared equals 34.64 t. Divide each side by t, I get 5t equals 34.64. So t, divide each side by 5, and I get it is in the air for 6.93 seconds. So that is my time. And if that's my time in the y direction, it's also my time in the x direction. So as long as it's moving up and down, it's also moving horizontally. So how far away does it land? I can use equation 1. I could also use equation 4 again if I wish. Delta x, that's what I'm looking for, equals v naught times t, so it's going 20 times 6.93. And if the acceleration in the x direction is 0, this term cancels. So my delta x is just 20 times 6.93. So this thing will land 138.6 meters away. And that is my delta x up here, 138.6. And I can solve for my final y and all that, but I don't care. It's asking me for this. I found this, so I have done my share here. So basically, if we want to figure out how far away it's going to land, you need to know from the y components. Remember, the y basically tells you how long it stays in the air. The longer it stays in the air, the more time it has to travel horizontally. So you need to find that to find out how far it goes. And again, we analyze the x's and y's completely separately. This 40 meters per second at the beginning was at an angle, so I had to break it down into its components, which, again, look back at an earlier video if you're having trouble with that. And then it was just like the horizontal velocity problems. All right, so until next time, I am Derek Genova. Have a delightful day.